Well, good morning, everyone, and thank you so much for that intro. It actually saves me a lot of talking, so that makes me happy. So my name is Sami. This is Tyler and Alex, and we're just going to very quickly take you through the work we've done this summer. Our project was the autonomous free-flying drones for use for spacecraft inspection, or in this case, cylinders. Everyone who's involved, you've heard about us. You met Cesar, who's our lead mentor, Sui and Marco from the NIA, who unfortunately couldn't be here. I believe Marco's on vacation and Sui's out at flight test. Chester's in the back, who's been pivotal in the computer vision work, and then Chris Mandarino, also from University of Pittsburgh, who's been a big help this summer. So just a quick outline of what we're going to present today. We're going to go over the problem statement we were given in our proposed system architecture. Tyler's going to go ahead and talk a little bit about the system components and his work with CFS. I'm going to then go and talk a little more about the drones and what we actually had to do to interface with the drones and the onboard cameras. And lastly, Tyler's going to go into a little more depth on the computer vision that we used. And finally, I'll walk... Alex, excuse me. Alex. I'm doing that a lot lately. I'm going to do a quick overview of what you're expected to see during the demo, and then we're going to walk over to the observation room to actually watch the demo. Excellent. So the problem statement, we were told to develop a system that will allow multiple UAVs or drones to do autonomous inspection with minimal external guidance or input. These drones are supposed to be used to simulate free-flying spacecraft such as CubeSats. The main focus was for these drones to use computer vision to detect damage seen on the objects in question. And we were using 2 cylinders provided to us by an external branch. And then the other main caveat was that we had to use the open source architecture ICAROUS, developed by this branch, for the software that allowed us to control the drones, the Vicon system, and basically everything that you see running in the demo. So I'm going to hand it over to Tyler to talk about the system.
All right, thanks. Okay, so just to kind of get us started here, I'm going to give a little overview of what all is involved with our system, and specifically this is how it's going to look within the demo itself. So what you see here is we have our computer, which serves as our ground station, which is able to communicate with the drones directly. We have our Vicon system, which simulates for us our GPS and our positioning. And then the two drones are also able to collaborate directly with each other using onboard computers. In our particular instance, we use 2 separate computers and run the instances directly on these NUCs. However, those NUCs could also be set directly on the drones themselves. So in this case, we could pass a flight plan through this system, and then the instances running on each particular drone are able to distribute them among themselves. And I'm going to get into a little more detail about how that actually works. So in order to enable this sort of demonstration, we have to have a software framework that we can start with. So what we start with is NASA's core flight system software, which is used for collaborative free flyer agents and such. And built on top of that, we use ICAROUS, which is developed within the branch, which is the independent configurable architecture for reliable operations of unmanned systems. And what this basically does is it allows us to add features very quickly through the use of applications. And then these applications are able to publish messages to each other over a software bus that so they're able to communicate directly. Just to give you an idea, this is kind of where we started, and then I'm going to introduce what we added. So basically, what you see here is we have all the applications within ICAROUS itself, and then they all have this communication layer, whether that be either through something like DDS or software bus network or something like that. So we have the ground station interfaces with its own application, so this is how we can bring in external components as well. Okay, and this is kind of the meat of what we've been working on this summer. So primarily, what we see here is we have one instance of CFS outlined in the green box, and this is supposed to illustrate the data flow, what is actually happening. So we have our ground station here. We'll upload flight plans into CFS, and at that point we have a flight distribution and controls the coordination of the actual drones and to distribute it the way we want them to. From there, it moves on to an app called Cognition, and what Cognition does is it basically has a high-level view of what the drone's particular job is to do. And then from there, we have guidance, and guidance is used to say, okay, so we have Cognition is giving me information about where I need to go. So guidance is going to give us raw commands about how do we need to maneuver in order to get there. So, and then from there, guidance will also rely on a positioning system of some sort, and most of the time that could be GPS. ICAROUS requires GPS. However, in this situation, we don't have GPS, so we simulate GPS via Vicon. So we have a Vicon system, which will give us. I'm going to go over that a little bit more in detail after this, but it pretty much gives us the position information that we need, rotation, etc. And then we can pipe that through so the guidance can see, okay, well, you're over here, so you need to be corrected to make sure that you're following the paths, and it'll give us the velocities and orientation in order to get the drone where it's designed to go. And then we have a drone interface. This again, for our case, we specifically made it for the AR2 drone, but I'll sub that out with a new app that would be more specific to whatever drone you're working with. In our case, the drone API we actually don't have in CFS, but there are, because it's a Python base, and ICAROUS cannot use the Python base structure. But there is a C base that could be ported for that. And what happens is we have the drone interface send the information to the API where it actually physically controls the drone, and then the camera will pipe back into CFS where computer vision is entirely wrapped into the structure itself. And then we're able to detect damage and such that way. So like I said, the Vicon system is just an indoor positioning and localization system. We use it to simulate GPS. Basically what happens is we're just capturing 3D frames of the entire room. So from that we see how if we just take a series of screenshots, basically we can calculate what kind of velocity changes there were if it was here and then it moved over there, so we know what it took to get to that point. And we have to make sure that we do a conversion from northeast down into GPS coordinates, and this is also done within ICAROUS. Just to give you some sort of visualization on this, this is kind of what the Vicon system looks like. All those green squares represent all the cameras. At all times you need to have 3 cameras pointing at the object to get a close-up. These are actually the Vicon trackers that are on the drone itself. And during the demo, keep an eye out for this on the bottom screens. You'll actually see these moving around. This is kind of what it looks like in the flight room. The camera's up top and all around the room. So to kind of summarize what we have done as far as software goes, so we introduced a Vicon app that can be used for positioning. We have a drone interface app, which allows you to interface with any drone or any API that you wish. We have what we call, Alex has called Sky Eye, which is our computer vision application for damage detection. And then we have our multi-agent path planning distribution application, which is very tunable. So we have one configuration set up that we'll be demoing for you later. And then also in this process, we've brought in some external SDKs that we're able to work with, such as the AR drone API, Vicon data stream SDK, and then OpenCV is now within CFS2.
So now, time to talk about the hardware. Just go over the drones we're actually using. So I want to thank Eric Cooper and his branch for providing us with several of these drones, the AR 2.0 drones made by Parrot. These are small, very versatile drones that actually, what's nice is they come with this big protective cover here on the side, which means it's very safe to work with them, great for indoor flight. As you can see, there's actually a lot of these shiny silver balls attached to the cover. Those are the Vicon trackers. Those reflect infrared light, and they're what allows the system to track. Obviously, the more trackers you have, the easier and more precise your measurements are. So both of the drones currently have 5 trackers on them in very specific different locations. This is actually just a photo of the drone itself. This is drone number 20. The other drone we're using is Droney Stark. We got to name them. We had some fun with that. It was great. So very quickly, looking at the drones themselves, they are Cortex-based computers. They run a subversion of Linux as their operating system, which means you're able to SSH in or telnet in and completely configure the file system as you need, which is extremely useful. They're Wi-Fi equipped, BGN, just 2.4 gigahertz, no 5 gigahertz support. This is important because in the flight space, there's actually a Wi-Fi network that we use to connect to the drones. And so the drones are configured to connect to the network automatically, so we don't need to log in every time or run the startup script. Makes testing much faster. The drones are also equipped with 3-axis gyro and accelerometer, which is great because they're able to give feedback on their movements in real time. That's very important for flight controllers, which I'll talk about later. And then the other big thing is there's 2 cameras on the drones. Front-facing, there's a 720p HD camera that outputs video at 30 frames per second. That's what we're using for the inspection of the cylinders. There's also a vertical downward-facing camera that's 60 frames per second, which is used for ground speed tracking and optical flow, which is really important for stabilization of the drone. In this case, it's very important that the drone is stable as it's flying around because of the video. If the video is shaky, we found it's never good for computer vision. We like to provide good data. As Tyler mentioned briefly, we needed to have a proxy for the onboard computing for the drones. These drones are small. They can carry up to 100 grams of extra payload, which is not a lot. Maybe a compute stick or an extra sensor. In our case, we decided we needed something a little more to do the computer vision, so we decided to take one of these Intel NUCs, or next unit of computing, as they call it, because there are several drones here that are equipped with these, and this is something that could easily be implemented. So not only did these NUCs serve as a ground station, they also served as the onboard computer that could be on one of these drones, a companion computer. These are equipped with i5 Intel core processors, which was really great for both running the CFS software and running the computer vision. And they connected to that same network that the drones were on using a standard TCP/IP connection. So everything was on one combined network. Next was the drone APIs. So the nice thing about these AR drones is that they are widely used for research, and there are APIs available in both C++ and Python to interface with them. In our case, we started using C++ and came across some issues with the API package we were using. CFS is also a C-based system, and so when we started doing the conversion, we decided let's just go to Python to start with for rapid prototyping. The other thing is we already had an instance of OpenCV working in Python, and Drone API actually uses OpenCV for a lot of its video processing. That's just what's been provided by the company. So there's a video client, which is OpenCV supported, which is actually what we use to pull video data live off the drone and send it back using a UDP connection. The API also supports navigation, feedback, and AT commands. AT commands are just another standard command structure used in UAV systems. And the drone actually has, the API has a layer of abstraction, which allows you to set these types of commands and then converts them to drone-specific commands. So that's a takeoff and land command, which we use automatically in the system. A movement command, which is, do you want to move forward, backward, left, right, up, down, clockwise, counterclockwise, sit down, reverse. And those directly control the roll, pitch, yaw, and gas, or thrust of the drone. And then hover and an emergency mode. And these two are great because the hover allows for internal stabilization. So the drone has its own controller that makes sure it stays put. And the emergency mode is necessary in case something goes wrong, and we're able to cut power to all motors. Very important to have when there are human testers in the room. Quick diagram of the drone system. Of course, there's the application level, which we have access to using any kind of computer interface. There's also the drone library here. This is what I'm interfacing with using the API. Notice there is a really nice control engine built for these drones. However, you can only use it if you have one of the applications provided by the company. We don't have that because I really didn't want to fly the drones using my iPhone the entire time. So we had to skip all of that and make up a lot of the software that was written in there ourselves. I ended up writing our own motion controller for the drone. There are 4 axes of movement. I'm sure everyone's familiar with roll, pitch, and yaw for aircrafts. So the roll, in this case, correlated to velocity and position in the X in the Y direction. Pitch correlated to velocity in the X direction, forward and backward. Thrust was velocity in the Z direction, so up and down, what the altitude was. And then yaw, which way the drone was actually facing, was equated to theta. And that was important because we had to make sure we could always focus where the drone was pointing. Because as the drone's flying around the room, obviously the object of interest is moving with relation to the drone, so we need to make sure we're always zeroed in on the cylinders. Another thing that I mentioned earlier, for the forward-facing camera, your pitch affects your field of view because the camera's on the front of the drone. So you have to make sure your pitch is as stable as possible and your drone is as stable as possible in order to receive the best video. So that we actually had to tune quite a bit. And just some diagrams of the different kind of flight characteristics and motor characteristics for different movement. Something that was really helpful to understand while designing our own controllers. So a bunch of different fun controllers ended up being used for these. There are some wonderful technical terms for them, but they're very simple. Originally, we had a PID loop for the high-level control, just all actions of the drone itself. Breaking it down a little more for the ground speed, so our velocity in the X and Y direction, we just used a simple proportional controller. So based on the speed the drone had to go, a certain roll pitch yaw, or certain roll and pitch were set to make sure the drone would meet the required output. For altitude, a simple bang-bang controller, which is just on-off. The drone was lower than where it needed to go up. If the drone was higher, drop down. And for the yaw, a double set point controller, which is basically two of the bang-bang controller. Two different speeds of turning the drone to focus on the object in question. The reason we did that is because when the drone starts, it's obviously not pointing the right way. It needs to get to the right point of view fast. And so it moves really fast to focus in on the cylinder. And then as the drone is slowly moving around the cylinder, we don't want it moving fast again, trying to re-localize itself. So we apply very subtle changes to the yaw to make sure the transition is as smooth as possible and doesn't interrupt the video stream. And then the last thing was actually converting everything from the global frame, which ICAROUS provides, to the local frame or the drone body frame. And that was done using standard rotation matrices from kinematics. So path planning, this was interesting because originally when we started doing our testing, we would open up Google Maps and start putting drop points and saying, let's have the drone fly here, here, here. That's not very accurate and it doesn't look nice on a map. You don't get perfect circles that way. So I ended up writing a script that would actually go ahead and take the coordinates you want from a 3D Cartesian space and convert them to geodesic coordinates, latitude, longitude, altitude. And that was done using an open source library to simulate the 3D projection from lat-long to a XYZ coordinate ring. And then what I did is we basically had the program generate a perfect circle and then convert those to GPS coordinates so that the flight plans would be as smooth as possible. That would actually give us a flight plan like that, which is a very neat looking circle. In terms of altitude and yaw, the altitude in our case was hard set based on the object. As you'll see in a second, I'll talk about the demo. There's multiple heights to our object. We've stacked two cylinders together, so there's multiple areas of interest in terms of altitude. So our drone, we would actually hard set, this is what the top of the cylinder is, this is what the bottom of the cylinder is, figure out the rest. And then the yaw, we'd actually have to determine our point of interest, which was the cylinder. What was nice is we put the cylinder near the center of the room and actually had a position marker for it. And so our system, using very, very simple trigonometry, would figure out what angle do I need to be facing at to face the cylinder in question. And that's something we'd pipe in as desired yaw. Lastly, just touching on the coordination and flight distribution. So Tyler mentioned this a little bit. We worked this into the app. The idea was we wanted multiple drones to be doing this together, coordinated, cooperative inspection. And you want it to be scalable. You don't know how many drones you're going to have. You might have one drone or one free-flying agent performing an inspection, and suddenly a second one is available and it comes and joins in. Well, then how do you determine what each platform should do? Do you want them to be repetitive? Do you want them to split up the workload? How do you make sure they don't collide? It's a big no-no. So what we built as a system is we had an input of a single flight plan, basically a list of all the different places we needed to take sensor data for the cylinder. In this case, a bunch of GPS waypoints at different altitudes. And then the system would actually split that up into n flight plans based on the number of drones available. And that would, currently what we have it doing is splitting up based on altitude, because we figured the best way right now is to have the drones flying at different altitudes to avoid any kinds of issues. So once the system sees how many flight plans, how many drones there are, it determines the flight plans and sends those to the individual drone CFS instances. And that, again, as I said, is based just on number of drones, how many waypoints need to be done, how many waypoints have been reached, and altitude. And what the nice thing is that the system is always polling and seeing how many drones or how many free flyers are in the system. So suddenly, if there's two and a third one joins in, it recalculates the flight points based on how many more waypoints need to be visited and what has already been done. There were some challenges working with the drones, mostly just things around communication, issues with Wi-Fi, issues with interfacing with our computers, but we worked through them all pretty fast. All right, I'm going to hand it over to Alex now to finish talking about computer vision.
All right, so I'm going to talk about the computer vision aspect of the project. We developed a CFS application. So I'm going to go over the problem that we solved with this application, some of the experiments and the computer vision techniques we tried, and then the overall pipeline that we developed in the end, and then some of the challenges we encountered and the workarounds that we had to get through. So the problem is basically two-part. First, you want to segment the cylinder from the background. We want to know where the module is in the image. The second part of the problem is we want to detect where the damage is within the module that we've segmented. So we use a window-based approach and find windows of damage. And then we report the damage to the system. So some of the techniques we tried, computer vision techniques, Otsu thresholding, template matching, grab cut, Sobel edge detection, convolutional neural network. We painted the cylinders to make our algorithm more robust. We did color-based segmentation, and we're going to be working on 3D modeling for the next 2 weeks. So here's an example of the Otsu thresholding. You can see it gets the cylinder in white, but the problem with this technique is that it gets the background and the floor. So we didn't go with this technique, but this is the output and it's basically an adaptive thresholding on the intensity, which is why we use the grayscale image for this. Another technique we tried is template matching. So we took a template image of our cylinder and we searched for it in the whole image. There's 2 problems with this technique. First of all, the cylinder has the mirrored portion and the speckled portion, and so we have to use a different template depending on the view of the cylinder. The second problem with this technique is that depending on the distance you are from the cylinder, the template would have to change size. So if you want to perform a template matching search and you don't know what distance you're at, you need to perform different size templates, which is slow. And then you don't know which size template match you would want to use in the end. We tried this grab cut. I basically used this as a black box, but from what I understand, it's kind of an iterative refinement and iteratively hones in on the cylinder location it's sort of like a template as well. This is the output of the grab cut. The problem with the grab cut is it's kind of slow. It takes a long time to run, so we didn't use this. One thing that we found was very useful in the project was Sobel edge detection. From the initial approach with the template matching, we use the Sobel. Sobel has 2 components. You can decompose into vertical and horizontal edges. So we use the vertical edges to find the right and left side of the cylinder, and we use the horizontal edges to find the top and bottom of the cylinder. We didn't end up using that because we didn't use the template matching, but it was a nice first approach. We did use the Sobel for false damage detection and removal. So later on, I'll talk about convolutional neural network, and some places that it thinks are not damaged really were damaged, or some places it thinks that are damaged really weren't damaged, and the Sobel helps remove the outliers. And then eventually we use it independently also as a filter to isolate the damage because it ended up being so robust. We used color-based segmentation after we painted the cylinders because we painted them a gold color like a spaceship would be painted, and just the single color made the background subtraction or the cylinder extraction very robust. And also the convolutional neural network was able to better train with a single color because it didn't have to train on the mirror and the speckled color at the same time. So here's the before and after of the damaged and the non-damaged cylinder with the paint. We just painted a primer and a color coat on both cylinders. Another tool we use is convolutional neural network. One thing we had to work on is generating a training data set. So what we did is we took images of the damaged and the non-damaged portions of the cylinder, and we used a sliding window approach to get several windows of identical size for input to the network. One thing we learned is not to use the sliding window to be very overlapping, or otherwise you get overfitting because it trains on too many similar images. Another thing I tried at first was generating synthetic data by modifying the brightness of the training data set, and that turns out that it wasn't necessary because the final network we used a brightness normalization, so it took care of that already. Here's just the output of the network on different windows. So this is the good cylinder, and all the green, each window is saying whether it finds damage, and here the red says this is damage that was found, and the green was not found damage. We trained two different neural networks. The first was a convolutional neural network that was designed for an ImageNet problem, which is basically like 100 different classes of images, like cat, dog, car, house. And we took the last layer of the network and made it, first we made it 3 classes, which was damage, not damage cylinder, and background. Later we simplified it, and we just trained it on damage and not damage, and we used the color-based segmentation to remove the background. And when we trained it on just the 2 classes, it was a more robust model. To make it even more robust, we used a simpler network because just training on the 2 classes, and the ImageNet was a little bit complex for our problem, and it took too long to train, but we used a two-layer convolutional neural network we built from scratch in TensorFlow, and we were able to train that on the 2-class problem and quicker and with a more robust prediction. So this is the final 2-class network we trained end to end. This is the Sobel filtering that we also performed. So you can see the Sobel finds a window of the damage, and the whole cylinder is segmented here, and this is no damage found, no damage found. And we highlight the damage by superimposing the Sobel filter result on the damage that we found as well. So for multi-cylinder segmentation, we had to remove the middle part, and we did that by recognizing that the clamps had a lower intensity than the surrounding gold color, so we could remove the middle and then run our algorithm on the top and bottom cylinder. And this just shows both results for the top and bottom cylinder. We'll demonstrate this in the demo after. So this is the overall pipeline where we chose the tools that work best for us and apply them in a pipeline. We performed the multi-cylinder segmentation by doing the color matching, basically. And so the gold color was, nothing else in the room was gold, so it was good to stand out against the background. We separated the vertical modules, the cylinder modules, by removing the clamps. And we did damage detection with the sliding window neural network. So we applied our neural network on different windows of the image to detect whether there's damage or not. And we used the Sobel for outlier removal because the Sobel was good at finding the damage because the damage corresponded with lines or Sobel lines in the image. So some of the challenges with the computer vision and what we did to solve them. One challenge is that when the app gets the video data, then it interferes with navigation commands. So we had to send the video data a different way to the app when we used UDP to do that. The UDP packet size is smaller than an image, so we had to break the image into different pieces and send it to the app one piece at a time. And sometimes UDP drops packages, so it required synchronization between the UDP source and the app that was receiving the images. When we got the images, then we pieced them back together and ran the algorithm on the images. Another problem that we found is running the convolutional neural network over windows, many windows where the damage could be present, took a long time because we ran it over like 50 windows perhaps to start. So we increased the stride of the filter, and then we ran it over less windows. And then that enabled it to run faster. Also, if we use the Sobel exclusively and just cut out the convolutional neural network, the Sobel works pretty good and it's a lot faster. We tried to use OpenMP to speed up the running the convolutional neural network over the windows, and basically we sent each window to a different thread. Right now it's prohibitively computationally expensive. The reason is because the windows are overlapping, so we had to share data between the threads, so we had to do a deep copy to each thread. If we have non-overlapping windows, I'd like to try that with the OpenMP, then we can just send a pointer to each thread, and then we wouldn't share so much data, and it might be fast enough, and we might eliminate the overhead and get a speed up with the parallelization. So the next 2 weeks I'm going to be doing 3D modeling. There's 2 tools we can use in the OpenMVG. One tool will take our Vicon poses and use that to reconstruct a 3D image so it'll know where the images were taken. The other tool actually can get the structure just from the motion. If we take a lot of images around the cylinder, the motion can be used to infer the structure. And we're also going to try an Alice Vision meshwork tool, which is a little bit more hands-off and might be more automated if we can't get these to work.
Just going to quickly go over the demo. So from upstairs in the observation deck, this is what you're going to be able to see. Into the room, we have our wonderfully padded foam floor that is very random on purpose. That helps with optical flow. And we have our 2 cylinders that are stacked up in the center of the room. And we actually will have 2 drones that will be going through and doing various flight plans. And so there's going to be a single flight demo. It'll be 2 drones, dual drones, and cooperative inspection. And so the bounds for it, basically there's been 1 flight plan that has been auto-generated by one of our scripts, so it wasn't handpicked. The requirement was that each cylinder has to be orbited a minimum of 2 times in order to collect enough vision data and say there was some other data we needed to collect while in space. And then a view of both cylinders is also required to look for damage in between them. So at some point, a drone has to go at a mid-altitude between the 2 cylinders to get a view of both of them at once. And so the actual flight you're going to see implemented, we're going to start with a single drone that's going to take off and start orbiting the cylinders at a high altitude. So it's taking a look at the top cylinder, which is damaged. Then at a random time, we're going to start a second drone that's going to go, it's going to join in, and it's going to be given a flight plan to start following waypoints at the lower altitude, because that's currently how we split it up. And so the drone will start orbiting the cylinders at the second or the lower altitude. After that, after it's gone around maybe once or 1.5 times, we're going to hit a button that will make it abruptly leave and exit the flight space. And when that happens, drone 1 is going to be notified, the CFS instance will be notified, well, there's no longer 2 drones, there's only 1. And it will be, the algorithm will basically tell it, there's all of these unmarked waypoints that haven't been visited yet, please go and continue collecting data for drone 2. So that's the flight we're going to show you. The total time should be a couple minutes of actual flight.
You'll see from the demo, it's essentially real time. It can process the frame, so it looks really, it's like streams real time.
So the drone is going to go ahead and climb to the higher altitude, and it's already seeing damage. Excellent. So we're running both vision techniques. If you see on the monitor, on the left is the entire detection with a neural network. On the right is just the Sobel detection, showing the actual lines of damage. And so right now, the white drone is actually told to sit in a holding pattern because it's detected the second drone has connected. And so it's just going to keep flying those waypoints up top until it reaches the minimum required number of scans. Got it. Excellent. No, no. All right. We're going to let it do a full orbit, and then we're going to have the second drone enter the fray. We have the vision from the second drone as well on the other monitor. I'm sure everyone has seen that. Just looking. Sorry. All right. Second drone has started, and it's going to start going around the lower waypoints. As you can see, it currently detects no damage because the bottom cylinder is the pristine one. Great. So the drone did one full orbit. It did not complete the second orbit as required. So you're going to see the first drone that's flying up high slowly start to descend its altitude and start taking over the waypoints for the second drone. Excellent. So the drone is slowly descending, making sure it's getting that 2-cylinder view. And then it's going to do one final lap to take over for the second drone, which did not complete its mission. All right, so the drone reached the lower altitude. Now it's doing the waypoints from the other drone. And once it's done, it will automatically land itself.